All right, there's one more complication I've got to put in. Often when we're talking about doubly reinforced concrete beams, we're talking about beams which have a lot of steel in them. And so there comes a point where you can't get all the steel in one bottom row. So you need to throw the steel in two rows. Okay? And that, as you appreciate, changes the lever arm. Okay? So you need to take the centroid of all that steel as the lever arm. Now normally when if it was just the black, you take it down to the center point of the bars. If it's the black and the red, you have to find the centroid of that. If it was, say, 4 bars in each, then it's the midpoint. That's easy. If those two aren't there, then it drops a little bit closer to that. But you've got to find that. All right? All right, let's have a crack at the problem then. Okay, when you have to make a beam with a certain mu naught, let's say you need to make a beam with 500 kilonewton meters of force, okay? That's your target mu naught. First thing I would do is say, get a spreadsheet or something so you can try out different numbers, all right? But you've got a fixed B, you've got a fixed D, and you're not allowed to go bigger than that, okay? And you try out the maximum amount of steel, and there's a formula for the maximum amount of steel you can put in, and you find out that's not going to make that, all right? So the steps you go through are, 1, find mu naught with maximum Ku, okay? Ku being a maximum 0.36 or 0.4 in the old code. Go ahead, use that equation. So I use this equation, put 0.36 there, and you know what concrete strength you're using, so those two numbers come out. You know what that is, you know what that is, you know what those two are. Rearrange it to get the area of steel, and you will find out what is the area of steel for that maximum Ku of 0.36. So that's the first step you do, okay? Second step then is to put that area of steel into this equation, and that, you know the area of steel, I've just found it. There's the yield, there's the lever arm, all those other things you know, that comes from the concrete strength, that is the concrete strength. You know those dimensions, you know that, you know that. So you find out the mu naught with the maximum Ku. That is, in a singly reinforced beam, what's the most that singly reinforced beam could hold? Okay? Remember there's phi in there too, don't get lost with that. Okay? Second step then is, then we need to add some secondary steel. Sorry, we're going to do it. We need to add some compression and some tension steel. Okay? So the first thing is, let's see if that top steel yields. So you put it in a certain distance, there's the cover, centroid, do the triangles and find out if that strain is greater than or less than the 0.0025. Okay? So you see if the top steel yields. When you've done that, then let's say we have a stress, let's pretend it had not yielded, and that our stress in the top steel was 450. Okay? So we know our stress there equals 450. And this down the bottom has yielded, so we know our stress there equals 500. All right? Now, that was our target. Let's say our mu naught was, oh sorry, I'm going to say, has the steel yielded? I'll keep up with myself. Okay. Let's make that step 4. Actually, no, that'll be step 3. Let's do this, yeah. Okay. Find extra. All right. So step 1 was find the mu naught with the maximum Ku. That's what can the concrete beam carry. 2, find the extra capacity needed. So in our example, if we had 500 and that does 350, we need an extra 150. And we've got to find that from this secondary steel beam. Step 3, has the steel yielded? Okay, yes or no? We decided no, we've done the triangles. So next step 4 then, once you found the steel yielded, find the area of steel you need at the top. So we know the lever arm between the top steel and the bottom steel is that much. Let's give that another little D. That's our lever arm there. And the moment for that is going to be the force in the steel times the lever arm. Easy. There's, let's say that was, for the sake of example, 350. Therefore, the extra capacity you need is 150. That is 150. The force is what we're trying to find out. That we know. Okay? Now, once we've found out the force equals the stress. What's that equation? It's gone out of my head. The force, yes, the stress times the area. That's it. Force equals the stress times the area of steel. We know the force now. We know the stress because we worked it out from geometry. That's how we work out how much area of steel we have. Okay? But before we do that, we have to subtract off that 450 minus the alpha 2-FC. So let's put some numbers out of the air, and let's say that alpha 2-FC, if it was 32 ampere concrete, and that was 0.85, 32, this 27, okay? 450 minus 27 is 423, okay? That 423 goes into there. Do you want me to do this all neatly again? I'm sorry. So, let's put some numbers to it. If our beam was, let's say our beam was 600 deep, it's a big beam, okay? Our lever arm between the top steel and the bottom steel might be 500 millimeters. And our force was 150. Our moment required is 150. Our D equals 500. Can someone divide 150 by 500 for me? No, do 150. We need that Newton millimeters. 150 million divided by 500 millimeters, Newton millimeters, will give us a force in newtons. Anyone got a calculator here? No one's got a calculator. Oh yeah, thanks man. Sorry? 300,000. 300,000 newtons. Okay, 300,000 newtons is our force. Is our force in there. Force equals 300,000 newtons. Now, the force equals the stress times the area of steel. We decided our stress was 423 megapascals times the area in square millimeters. And our area equals, what's 300,000 divided by 423 now? 300,000 divided by 423?
709.22.
709 square millimeters. That is the area of steel I need up there. Okay? Now that force, 300,000, is also, I need to get to the bottom here. At the bottom, we can just use 500 megapascals. So take 300,000 and divide it by 500 for me. And we'll find it's 600. Okay? Mental arithmetic. All right. So we've worked out that the top steel That needs an area of 709, and the bottom steel needs an area of 600 square millimeters. So to design that beam for 500, you need whatever it is in the concrete beam, plus 709 at the top, plus 600 at the bottom. If you put that in, that will give you an MU naught more than 500. Does that make sense? Yep. Okay. I'll talk briefly about another reason that you'd put top steel in concrete. When you have a concrete beam, let's draw it over here. Let's have a concrete beam over here, and you put only bottom steel in. Okay? And let's pretend this beam is a roof. Okay, and you've got someone you love very much right here. Okay? Now, what do you guys know about concrete? What do you guys know about concrete? You pour it, what happens to it? Takes ages to set. What else?
Never dries, believe.
Oh, come on, it does. After 90 days, it's, it's as strong as it's going to be. Okay. What happens though? What else? Warp. Why? No, slump is a phrase used about wet concrete.
Oh, okay.
Do you know that concrete shrinks? Right. Concrete shrinks. Steel basically doesn't shrink. Okay? So if we assume that the steel is staying at the same temperature, the concrete shrinks and the steel does not. Okay. What's that going to do to that beam? What's it going to do to that beam? Yep. What will the cracks look like? Okay. What's happening if I do a cross section through the beam like this, okay, and we have a lot of steel there, so the whole thing is trying to shrink, and at the bottom it's got some steel nicely holding it and stopping and saying no thank you, you're not going to shrink. Okay, the whole thing bends, and actually the shrinkage is going to put a deflection in the beam like that. Oops. Okay, because the top's getting shorter, the bottom is staying the same length, therefore the beam is going to deflect. So a new engineer comes along and goes, holy moly, the beam is deflecting. We haven't even put any load up there, what's going on? The answer might be that the concrete is shrinking and causing that deflection. And so it looks like deflection under load, but it's actually a shrinkage load. Alright. While we're on beams, one-way slabs are exactly the same as beams. Okay? They're just very wide beams. Alright? In a slab, there's a slab there. You put your steel in, put your steel in the bottom. Again, it's the same thing, it's just a very wide beam. Okay? And without the rings. So one-way slabs, beams, you can use all the same set of equations, basically all the same assumptions. That's one-way slabs. There are two-way slabs, which are different kettle of fish. All right. Any questions on that?